Okay, this is the 8th video on exponentials and logarithms, where we're going to have a look at how we can use logarithms to turn power functions into straight line graphs. Because the whole idea is, straight line graphs are really easy to deal with. We can find gradients and intercepts and make predictions and draw them, and it's all really nice and simple. However, when it comes to power functions, we can draw them, but it's a lot more complicated. So we can use logarithms to turn complicated situations into simple situations. So before we get into that, let's just have a quick reminder of straight line graphs. We know they look like this, and we know that we could rewrite these. I could rewrite this in a different way. I could say that x equals my constant plus my gradient times x. Remember, this is exactly the same thing as this. Just worth bearing that in mind for something you might see later on in the video. The number you see by itself will always be the constant, the y-intercept, and the number in front of the x. Or, I mean, I could, in theory, I could write it as x times m if I wanted to. It's the same thing, right? So the number that multiplies the x is the gradient. So worth bearing that in mind for later in the video. Anyway, so like I say, polynomials could look something like this, where I've got y equals ax to the power of some number, so the x is in the base, and the power function, obviously the x is in the power, that's what makes it the power function. So these are the two types of questions that you might be dealing with here. I'm going to do an example of both of them. Before we look at the examples, let me just show you what I mean by transforming them. So, if I was to take a logarithm of both sides here, so if I was to take log of the left-hand side, I've got log of y. I'm just doing log base 10 here. So log, you could use other bases if you prefer. So log base 10 of y equals log base 10 of a times x to the power n. Now, using the laws of logarithms, I could split this up into two different logarithms. So log of a plus log of x to the power n. So just splitting this up into an addition, which I could then go one step further and say, right, so log of y equals log of a plus n times log of x. So I've turned this into this. And the whole point of this is, if I now plot log y on my y-axis, so rather than plotting the y values, if I do log of all of the y values and plot them on my y-axis, and then rather than doing the x values on the x-axis, if I do log x on my x-axis, then this is a straight line, because I've got y, what's on my y-axis, equals mx, what's on my x-axis, plus c, my intercept. So in the context of this question, the n, the power here, would be given by the gradient of my straight line, and this would be my y-intercept. You'll probably see it a bit more clearly when we look at an example, but hopefully you can see. If I plot this on my y-axis and this on my x-axis, then I've got my mx plus c. Let's have a look at the other one. So over here, again, take logarithms of both sides. So log of y equals log of a b to the x. So log of y equals log of a plus log of b to the power x. And I can now put my x at the front. So log of y equals log of a plus x times log of b. And again now, in this case, my two variables, x and y, if I put this on my y-axis, so again, rather than plotting the y values, I will get my calculator and do log of all of the y values, and then plot those on my y-axis. So this is on my y-axis. In this case, I can plot my usual x values. I don't need to do the logarithms because it's just straight up x. There's no log of the x. So I can just put the x values on as usual. But this is my x. So y equals x. This would be my m. And this is going to be my c. Right. So that's sort of the mathematical theory behind it. Let's have a look at a couple of examples that might make it a bit clearer. So, it says, a scientist records the following data for variables x and y. So I've got x, 1, 2, 3, 4, 5. Y is 200, 1,600, and so on. And you can see I've got an extra row at the bottom there for log to the base 10 of y. She thinks that a relationship between x and y may be modelled by y equals kb to the power x. So y equals kb to the power x. So like I just showed a couple of moments ago, I could rewrite that. I could rewrite that as log of y equals log of kb to the power x, which then allows me to rewrite it as log of k plus log of bx, and then the x can come to the front. Like that. Okay, so this power function here, by taking logarithms of both sides, I could turn it into this, which will be useful in a moment. Right, so part A says complete the table giving you answers to two significant figures. So what I'm going to do with my calculator, I'm going to do log to the base 10 of 200. So let's see that. That's going to give me 2.3 to two significant figures. Now do log of 1600 and I get 3.2. Log of 4200, 3.6. Log of 1700, 4.2, and log of 6900. There we go. So part A done. Part B, on a grid, plot the values of log to the base 10 of y against the values of x. So I'm going to have x on my x-axis, and I'm going to have log to the base 10 of y on my y-axis. So x is 1, 2, 3, 4, 5. And then my log to the base 10 of y, so going up my y-axis here, so if I say that's 1, 2, 3, 4, 5. And then I'm going to go, so when x is 1, y is, log to the base 10 of y is 2.3. So 1 and 2.3 is about there. 2 and 3.2 is there. 3 and 3.6 is there. 4 and 4.2 is there. And 5 and 4.8 is there. Part C, by drawing a line of best fit, find the values of k and b, given my answers to two significant figures. So I can draw my line of best fit, which is going to look something like that, I think. I think it's going to be something like that. Maybe, yeah, something like that. Right, so I draw my line of best fit. Done. Now I need to find the values of k and b. So that's where this comes in. So, looking at my equation here, this, maybe if I highlight this. This is on my y-axis, that's my y. This is on my x-axis, which means that this is my gradient, because it's the mx. So my gradient, so log b is my gradient of this line. So let's work out the gradient. So the gradient's the change in y divided by the change in x. So the change in y, I think I'm going from about 4.8 is my y coordinate here. My y coordinate here is about 1.6, I think. So this is the change in the y coordinates. The change in the x coordinates is 5 minus 0. So log b equals 3.2 over 5. So log of b equals 16 over 25. And now if I do the power function of both sides, so b equals, remember log when it's written like that, that's like base 10. I took base 10 log to base 10 from before. So this will be 10 to the power of 16 over 25, which is 4.37. To two significant figures, I think the question said. Yeah. So there we go. So the fact that this is my gradient, my log to the base b, log to the base 10 of b, that's my gradient. I knew that because it was in front of the x. I could work out the gradient of the line and work out what b is from there. In terms of k, well that here is the constant by itself. So I know that log of k is my y-intercept, which I reckon is 1.6. So same idea. If I now do k equals 10 to the power 1.6, so to get rid of the log here, just do 10 to the power. And if I do that, I get 39.8. So to two significant figures, that is 40 to two significant figures. So there we go. Second example looks like this. It says the relationship between y and x is modelled by y equals a x to the power n, where a and n are constants. Show that the relationship y equals a x to the power n can be expressed in this form, giving m and c in terms of a and n. So, going to go through the process that I've been through a couple of times already, but let's do it. So y equals a, so let's take the log to the base 10 of the left hand side, and then log to the base 10 of the right hand side. Let's split the right hand side up using the laws of logarithms. And now use the power law. To bring the n to the front. Like so. Now let's just compare that and that. So just comparing this now. In order for these two things to be the same, I can see I've got a plus c constant on the end. So that means that c is going to need to be this. This is my constant. So c equals log to the base 10 of a. And their m that's in front of the log to the base 10 of x, their m is my n. So the gradient m is my n there. Right. Next part of the question. The graph shows the line of best fit for values of log to the base 10 of y plotted against log to the base 10 values of x. Yeah, so you can see in this question we've got log to the base 10 of y like we had in the last question, but look, on my x-axis now, I've got log to the base 10 of x, rather than in the last example I just had the x values. And we've seen why, because in this case here, I'm plotting log to the base 10 of x, not just the x that I had before. So that's important. Okay, there it is, part B, find the values of a and n. So, same as what I did a couple of moments ago. If I, first of all, the y-intercept there looks to me to be about 1.5. So, if my y-intercept is 1.5, that must mean that log to the base 10 of a must be 1.5. So a is 10 to the power 1.5, which is 31.6. And then for the value of n, well, I know that's going to be my gradient. So let's work out the gradient of the line here. It's going to be very rough. So I think that's about 4.5 there. This is about 1.5. So 4.5 minus 1.5 divided by the change in the x coordinates is 0.6, take away 0. So what's that? That's 3 divided by 0.6. Which I think is 5. So my value of n is 5, because n was directly the gradient in this example. And finally, part C. Find the value of y when x is 1.1. Well, now we know what a and n are. We could actually go back to the original equation that we started with, which was y. Remember, the original equation was y equals x. A x to the power n. That was the original equation we started with. And I know these values now. I know that a is 31.6. And I know that n is 5. So now I know that information, I can work this out easily, because all I need to do is go y equals 31.6 multiplied by 1.1 to the power 5. So just put the 1.1 in there instead of x. And what do we get? Is 50.9. And there we go. So, two examples. One where we have the x in the base. One where we have the x in the power. But in both examples, we've taken the log of both sides and turned them both into linear equations. So make sure you fully understand these steps here. Watch the video again if you need to see how we can turn this into this, or how we can turn that into the similar sort of equation. And make sure you understand why it is that this represents the y-intercept and this represents the gradient, because that's really important and really useful if you can do that.